So welcome to lecture 36. This is going to be on MOS inspection analysis. We've been doing bipolar all this time, and I haven't been doing much MOS, and you'll see why. It's because MOS is kind of a subset of bipolar. If you know bipolar, you know MOS in terms of small signal analysis. But first, some announcements. So homework number 11, you've seen it's online. It's going to be due Friday the 4th. That's 2 weeks from now, actually, so you have nothing due during the Thanksgiving break. Homework 11 will actually be your last homework assignment. You're not going to get another one after that. And that's to give you a break because your lab number 6 you're also working on in parallel with that. And that's going to be due Friday the 11th, which is the last day of the RRR week. I should say that this week, though, in lab, you have your first checkpoint due. And so I should say that. So first lab number 6 checkpoint due this week in your lab section. That's just a spice. That's just a spice design for your lab. Today is the only lecture this week. Since Wednesday is a non-instructional day, and Friday, of course, is during Thanksgiving break. I guess the last thing I'll say is you should have received an email with your Z-score in it. And so I sent Z-scores to everyone in the class, and those are the Z-scores according to my Excel sheet. And so you know all your grades through GradeScope and that sort of thing, so you can see all that. And so hopefully if there are any errors made in that thing, you'll get it corrected with the GSIs. But in terms of calculating the Z, I'm using the exact formula that I had given you the first day of class, and which we'll talk about right now a little bit. And so this is the grading and normalization procedure. This is a handout that's online. It's been online since the beginning of class. If you want to know exactly how Z's are computed and how Z's are used, you can go ahead and read this, but I'm going to go through a little bit of it for you. And so what a Z-score is basically turning your grade into an average and a standard deviation from the class. And so, for example, if you got a grade G sub I on something, to get the Z-score, you subtract the average of the class and divide that by the standard deviation of the class. And what that does, it turns your grade into a number, a much smaller number. And so a number that is 0 if you're exactly at the class average, and that is +1 if you are 1 standard deviation above the class average, and -1 if you are a standard deviation below the class average. And so all of these things together allow one to assign grades to the class, which is basically being done on a curve, but it's a pretty gentle curve, I would say, in this upper division EE class. And so when I say that it's gentle, what a lot of people want to do, want me to say, is what exactly is this Z-score? What grade does it correspond to? And that's something that over time, I guess I've been able to better predict, but I can't predict completely on these things. And so I'll give you some information on that, but I won't be able to give you the exact numbers on that. But let me wait till the end to do that here. So this is how we compute the Z-scores, and then for each of the different things in this class, let me skip to the end of this. This is the breakdown of everything in the class. So your homework is 15%, your labs are 35%, your midterm was 20%, your final would be 30% of the class grade there. So your lab, you can see, is a big percentage of that class grade, and so that's distributed over a lot of different work on that. But going back here, what we do is we get an average of all the homeworks, and we take a Z for your average homework score, which you have as an average. So all your homework scores, there's 11 of them, we'll take the average of that. We'll get the average of the total class and subtract these two divided by the standard deviation for the total class. That gives you a homework Z. And that gets multiplied then by this 0.15 to create that part of your overall Z-score, or your overall grade score. And we do the same thing for the midterm, for the final. For the labs, of course, we're also taking Z's for each of the labs there. And so this is lab 1, lab 2, lab 3, lab 4, lab 5, lab 6, etc. there. And then the thing is with labs, though, there's a little bit of variation because you have different TAs. And so each of your TAs is teaching their own sections. There may be some differences in how they're teaching the sections. There may be some differences in how they're grading your labs. And so because of that, in order to account for those differences, we not only take a Z for all of the stuff that you do in that particular section, but we normalize the two sections together as well by taking a Z for the whole class and taking the Z from each lab TA, dividing that by a standard deviation for the whole class. So there's a couple normalizations going on here to account for the fact that you have different TAs and different sections, and even the sections are occurring at different times and that sort of thing. And then finally, when all that's computed, we take this total weighted grade here, and then I take a Z of all of these things here, and that gives a final Z score. And that Z score, again, is going to be some number usually between -2 and +2 or something like that. And again, people like to ask questions like, well, what does this number mean? And so I think the best way I could say that is that historically, if you had a 0, Z, you probably got a B+ in the class. Okay, so that's where you end up with that. If you're a little above a 0, like say in the 0.4 or something range or something, 0.3, 0.4, that's probably an A- or something like that. If you're below that score, say you're down in the -0.5 or something like that, then that hits a B. So those are kind of the scores that correspond to these different things. And again, I cannot be absolute about this because it depends on where the curve is, and that's different for every year. But historically, that's what it ends up being. And so that's your grades. Those are your Z scores there, and I wanted to get those out to you at least by now so you can know where you stand in the class right now. Any questions about any of this from anyone? You can. I went through this fairly quickly, but you can download this from the website and read it on your own, and then calculate your own Z scores to make sure that I've got it right. You're going to need averages and that, so you can email me if you want averages and that sort of thing to do the calculation. But I don't think I've ever made a mistake in the past. So that's what your Z scores end up being. That's sort of what they mean in the end. Okay. All right. So. Let's get on to some of the lecture topics here. And so, because we don't have a Wednesday lecture, we actually don't have that many lectures left in this class. We've got a total of 4, it looks like. We've got this one this week, and then next week there's 3 lectures there. And so I do want to get to the digital stuff, and we'll do that next week. So today we'll sort of move in that direction by heading in the MOS direction. But before doing that, I want to finish off talking about this design we did last time that's similar to your lab but not exactly like it. I also want to then talk about MOS inspection analysis. And so last time we designed this. We did the DC biasing, which this is showing right here. We did the AC. We did the high frequency analysis. We did the whole problem there. So you have really all you need to do your lab number 6. We even started talking about this final stage here and how much voltage you'll have swinging around this final stage. So we talked about the fact that even though the voltage out here is swinging quite wide here, it's a large voltage compared to what one might expect for a small signal voltage. Everything is okay from a small signal sense because the voltage you're dropping across the base emitter is still very small compared to the thermal voltage, 25 millivolts. And you could say the same thing for Q2 as well in this. So in fact, if this is an emitter follower, which you've learned already, then it's got a gain of 1, which means if you're swinging 2 volts peak to peak out here, you got to be swinging 2 volts peak to peak here, which is the output of this stage Q2. And so same kind of thing. When Q2 is doing that, you don't have a very big variation in the VBE voltage right here. And that's what keeps small signal still legal in all of this. And so we did talk about that in detail and even have that right here. So this is that part of that lecture that did that. We basically said that if you got a gain of about 0.99, and if you have 1 volt here, you'll have 0.99 volts here, which means you drop about 10 millivolts across the VBE of Q3, and that is less than 26 millivolts. And so the other half of that I should also talk about is, you have this, you got to keep this signal small across Q3, but across the VBE, but the VCE of Q3, this voltage across here, that's quite large, what's spinning across that. And so Why is it that that's okay? And so let me spend just a little bit of time talking about that. So if I'm looking at this voltage, okay, so sorry about that. My computer just crashed. So I'm going to pick off from where we left off. The recording was still going, and it recorded at least 10 minutes of the opening. So I'm just going to go from where I started there, which was right here. I was talking about how the signal across VBE could be very small, but the signal going across VCE here, this signal, the VCE signal here, small signal VCE, may not really be a small signal anymore. And so how can we still use small signal analysis when VCE is moving so much? Well, what you need to remember is that the IV characteristic that we're worried about here is this one. And so this is now the total signal that I'm showing. So I'll do lowercase v capital CE there. And this is IC. Well, let me do the total signal here too. Oh, that's right. That is total signal. Okay, and so you know that the curve for this looks something like this. It goes like that. And so what you're seeing here is that this curve looks very linear over a fairly long range. So the curve over all this range of VCE here, curve looks linear. Well, I'll say the curve is linear. It's fairly linear throughout this whole range here, which means you can traverse this whole VCE and still be okay. So if I had a signal in the time domain that was doing this, you know, we're not violating any of our small signal parts here, because what small signal is trying to do is linearize things, and this curve is linear over that range. It's no longer a small signal, but it's still linear. So all of our analysis still works there. Where it goes nonlinear here is at this point. And remember, this point is where you start going from forward active into saturation. Right, this voltage here is the VCE saturation voltage there, which kind of tells you that in order to keep the signal linear across VCE, you have to make sure that VCE never goes lower than this VCE sat, which is about 0.2 volts. Right? If we start getting lower than this point right here, then we're going to start going nonlinear. And then our small signal analysis and everything no longer really works, and we have to use nonlinear equations for everything. But let's take a look at this more closely now. And so let's take a look at the last two stages of that amplifier we just designed. And let's sort of ask ourselves the question, what's the maximum voltage swing we can get at the output? Because that's one of the things you have to design for lab number 6. And so to determine this, you have to think in both small and large signal domains here. And again, our output here is an emitter follower, and that's an output stage now. And that's the nice thing about emitter followers. They have a low impedance, so they can drive low impedances here. And probably more importantly, they can deliver the current needed to drive that impedance. The current's going straight from VCC here and out into RL in this case. Actually out into both R3 and RL, since that looks like a short in the small signal sense. But let's take a closer look at this circuit and try to determine what's the signal swing, the largest signal swing we can get at the output here. And so to do that, the reason why I'm showing both of these stages is that this stage just has a unity gain. So whatever's going here is going to be going there as well. So it's really, the onus is really upon this stage here to be able to get that total voltage swing, because that's just going to be duplicated out here, as long as that voltage swing is above ground from RE3 right here. And so let's take a look at how you might attack this problem. One thing you want to do is determine what's the maximum swing you can get in this stage, and what's the minimum swing or minimum voltage you can get off of this stage, off of the collector here. And so to do that, take a look at just this thing. What is the maximum voltage you can get here? And so we'll call that VC2 max. Okay, and so the maximum voltage I can get here, obviously, I can go all the way up to VCC. And so my maximum voltage is simply going to be VCC in that case. And so now what I want to ask is, what is the minimum voltage that I can get on this point right here. And so let's go down here and write out that minimum voltage. So VC2 minimum, that's going to be equal to the voltage that keeps everything linear still. And so going back to the right side, I just drew this thing here with IC and VCE. And so I just said that I'll stay linear here as long as I'm above, as long as VCE is above VCE sat. And so what I want to do is ensure that I have at least VCE sat across V2. And so that means that the minimum voltage I can go down to is whatever VE2 is here, right? This voltage, whoops, what just happened? Let me go back to that. So whatever VE2 is right here, that's the voltage right at that node. And that, of course, is set by your biasing. That's going to determine the bottom voltage you can get, because that voltage is not going to change. That's a bias point there. And so I could say that VC2 min has to be equal to VE2 plus a VCE2 sat voltage. So it's about 0.2 volts higher than what VE2 is there. That's going to be my minimum voltage right here at that point. So I've now sort of talked about what my maximum and minimum voltages are. And so let me say one more thing about the maximum voltage that I get there. So let's take a look at first the case of a maximum voltage down here. And really talking about this up here. That's what I'm doing. And so if I have that, then if I were drawing a time domain signal and that was my output voltage here, this is coming up like that. And so what's happening at the output now is Q3 is sourcing enough current that goes into both R3 and RL that it can drive this voltage up to whatever that voltage needs to be up here. Okay, so what's happening here at that very point here, we're sort of making sure that Q3 sources enough current to push V naught up across the parallel combination of RE3 and load resistance RL there. Okay, and so in the end, that's the maximum voltage. Q3 has to source enough current, but it's got a lot of current it can source. It's taking its current directly from VCC. And that current, IE, is really going to be equal to the base current times beta there. And we should be able to get a lot of base current coming out of this as well. So in the end, what determines that maximum voltage there is really this Q2 stage and this VCC right there. So the maximum voltage limit is determined by that Q2 stage. And so now I can write an expression for what that maximum voltage is going to be there. It's going to be whatever the VE max is here. It's going to be whatever the maximum voltage here minus VBE is right there. So this voltage right here is going to be able to go all the way up to, if I wanted to write an expression for VE3 max. Okay, that's then going to be equal to VC2 max minus a VBE on, which to be specific is going to be the VBE on of device 3. And so that then is going to just be equal to VCC minus a VBE on voltage. So 0.7 volts below VCC is what that maximum voltage is going to be. And so, and that's because, right, dropped across here is just going to be VBE on. And we're talking about the total voltage drop across that, not just the small signal voltage drop there. So that's why we're thinking both in terms of small and large signal domains now to determine how much voltage excursion you can get at the output there. And so hopefully you can see that because this node here is limited to VCC, the maximum voltage you can get on this node here has got to be that VCC minus VBE, because you have to drop that VBE across the base to emitter junctions on this Q3 transistor. Okay, so that's the maximum voltage, but now I want this minimum voltage out here. I know what the minimum voltage is at Q2, and so that's going to dictate the minimum voltage at the output as well. And so at this output, I can go down here and write that VE3 minimum. That's got to be equal to whatever this VC2 minimum is. And so we know that that's equal to VE2 plus a VCE2 saturated there, and then minus VBE on. And to be specific, I'll say minus the VBE3 on. So it's just everything going minus that VBE. Whatever I get here is going to be duplicated out here, but VBE lower than that. Now, you got to be careful here because this is one maximum here, but if you bias this node such that VE2 is so small that the voltage out here, even though the voltage here could be doing a pure sinusoid, the voltage out here runs into ground, then you're going to have a smaller maximum excursion at the output here. So it's going to be this, or it's going to be 0 volts. If you actually drive the voltage here all the way down below ground. It can't go below ground, so it's gonna go to ground. 0 will be the minimum that you get there. Okay? And so that's what we have for this total excursion. And so in the end, I can look at this whole thing and say that therefore V out max, which is the maximum amplitude of voltage you can get. So if I complete that, it's going to be equal to VE3 max minus VE3 min divided by 2, where we've written equations now for both of these values here. Should have done that in blue. Maybe I'll still do this in blue here. So this VE3 min is right there, and that VE3 max is right there. Okay, so that's now your V out max, the maximum excursion you can get, which is that voltage there. Okay, so you're going to need to think about these things in your Lab 6 while you're doing it here. You need to think about, what is going to limit the voltage that you can get at your output, and that then will determine that particular spec in that lab. Okay, any questions about this? It's a little different. You have to think both large signal and small signal when you get to this point. Okay, so with that, let's move on and talk about the MOS situation here. And so in order to do that, so now we're talking about MOS small signal analysis and how to do that using inspection analysis. Hopefully now you have some comfort level with doing inspection analysis with bipolar junction transistors. To do it with MOS, we now really should just look at the differences between their small signal models. And if I had to point out the differences between these small signal models, I would basically say, here's one difference right here. I've got an open circuit there, whereas in this case, I have R pi. Okay, so that's one difference. And really what I could say is in this case, for the MOS case, R pi basically goes to infinity. And what's really happening in the end is that for a bipolar junction transistor, I have a beta. Whatever IB I get, IC is equal to beta times that IB. Right? For an MOS transistor, what is IG? It's equal to 0. At least at DC, it's equal to 0. And so I'm getting some finite current ID. If I wanted to say ID is equal to beta times IG, then that beta is going to have to be infinity. And so this R going to infinity really comes from beta going to infinity, because beta going to infinity means that R pi, which is equal to beta over GM, that also has to be infinity. Okay, so that's one difference between MOS and bipolar junction transistors, that you have an infinite beta in the MOS case. Other than that, there's no real difference between these small signal circuits, right? They look exactly the same. I would get anything that I did in bipolar, I can get for MOS by just making R pi going to infinity or making beta go to infinity. Now, there is one difference, and that's this GMB. And so that's an often neglected thing, but it can actually impact what we do in all of this. And so we will have to be careful, at least about that aspect, when we're doing MOS analysis. And so we'll pay attention to that in just a second. But for right now, let me just say that I can make the MOS model exactly the same as my bipolar model if I take this often neglected GMB VBS here and hook the MOS transistor up like this. And you've seen this before, where I'm now tying the source to the bulk. If I do this, then I make that VBS voltage equal to 0 volts. And in this case, it gets rid of GMB. It means GMB is not relevant, and so we can neglect it. So anytime we do this, we tie our source to our bulk, okay, we can neglect GMB. Okay, so with that backdrop, let's handle that as a first case. Now, we're not always going to be able to do this, so I will say this. We can't do this often. But it is a useful special case. And I'll talk a little later about why we can't do this often. But because of this, let's go ahead and take a look at this special case. So I'm going to do that on the right side here, or on the left side. And so here what I want to do is the same thing we did with bipolar transistors. I want to look at generalized loading. And so for now, like I said, we're going to ignore the body effect, assuming that our transistor is hooked up just as I showed, with the with the source tied to the bulk in this case. And so in this case, like I said, we're going to use the same inspection formulas as bipolar, but now take beta going to infinity, which means R pi goes to infinity. And so in order to determine the MOS equations here, I'm just going to use the bipolar equations. And so on this side, I'm just going to say, outright referring to the bipolar inspection formula sheet, which you all have. Okay, and I'm going to make a little chart here. So in the bipolar case, what was that? For some reason I'm writing horribly right now, so let me kind of clean that up. So in the bipolar case, we have an equation, and then from that equation, we should be able to just immediately derive the MOS case. So when I was looking into the base of my bipolar transistor, I got an input resistance equal to 1 over GM plus whatever resistance was hanging off of my emitter times beta plus 1. Well, to go to MOS, again, what I want to do is I want to make beta go to infinity. And so my MOS equation in this case, for the resistance seen looking into the gate of my MOS transistor, that's going to be infinity. And so what I just did was take a look at the resistance seen looking into the gate. So that's this resistor right here, which I'm going to call R little g. That little resistance there is that resistance looking into the gate. And so I'm going to use the same nomenclature as I did for bipolar. This thing I'll call R big G. as the resistance looking out of the gate in a generally loaded situation. And so on and so forth for the rest of these. So this is going to be R little d instead of R little c. This obviously is going to be R big D. You can see it hanging right there. And you see RS. In that case, R big S. And in this direction here, looking up that way, that's going to be my R little s. And we're going to want gains also from terminal to terminal. So we're doing everything that we did with the bipolar transistors, but we're not doing an inkling of work to do this. I'm not going to solve again by putting the MOS hybrid pi model into a generally loaded circuit and resolve that. I don't need to, because I just said that the two circuits are exactly the same as bipolar, except that R pi or beta goes to infinity. Okay, so I could take another equation from the bipolar case, the resistance looking up into the emitter, that was 1 over GM plus RB, whatever was hanging out of the base, looking out of the base, divided by beta plus 1. But again, beta goes to infinity. And so for the MOS case, RS is just going to be equal to 1 over GM, at least for this case where I've tied my bulk to my source. Okay? Very simple compared to bipolar. I don't even have to care what the source resistance was in this case. Finally, for RC, oops, R little c. What do we have for the bipolar case? Well, we had this equation that probably no one likes because it's a big equation and, you know, no one likes to memorize that much, but this was the equation. Okay, but R pi, of course, that's infinity now. And that happens when beta goes to infinity. And so now the resistance seen looking down into the drain of this circuit, this RD up here, now just reduces to R naught times 1 plus GM times whatever resistance is hanging off of the source. And so you can see that for MOS, the equations simplify. If you have the bipolar equations memorized, you have the MOS equations immediately by just taking beta to infinity. A very easy thing to do. Okay, that's why I like to teach bipolar first, then cover MOS. And in 140, MOS may be the more important device for you to be using because that's all integrated. But that inspection analysis you'll find for small signal is going to be even easier for bipolar than for bipolar. Okay, and so those are the resistances. Now let's just get the gains. And so I want the gain from, go back to black on this stage. Okay, I want the gain from my gate to my drain. Well, that's the same as the base to collector gain. And so this is going to take on the same equation. So that's GM times RD, where that RD is all of that resistance in shunt with that node. But remember, for the bipolar case, we had a certain equation for GM where the MOS case is going to be exactly the same. It's going to be GM over 1 over GM plus RS. Okay, and then another gain that we can get is from the source to the drain. So in this case, from here to up there, that was the same as emitter to collector gain for the bipolar case, but same circuit, so we're really going to get the same expression for that if we did the hybrid pi analysis. So that's going to be minus GM times RD. Remember, for the bipolar case, we had a ratio between a voltage divider between what resistance we had hanging off of the base and R pi. Well, in this case, R pi goes to infinity, so that voltage divider just goes to 1. So in this case, for MOS, it becomes very simple. The capital GM is just equal to minus little gm. You don't have to worry about any resistors around the MOS transistor in this case. And then finally, the gain from the gate to the source ends up being GM times RS, where for bipolar that was RE, divided by 1 plus GM times that RS. Again, that used to be RE. And so I can write this to make it similar to one of the equations we wrote for bipolar as RS divided by 1 over GM plus RS. And so that's it. Those are the equations for MOS inspection analysis right there, at least for the case where I have tied the bulk to the source. Okay, so I should say for all of these things, for VSB equal to 0 volts. Okay, and the same thing here. I should say that too. I've tied those two together. I've shorted them together. And obviously I keep saying that because that's going to affect us sometime in the future. But let's just go ahead and do a little MOS inspection analysis right here. First, and see what happens if we go ahead and use those equations without worrying about whether our source is tied to our bulk. And so in this case, what I'm going to do is borrow a planned circuit back here. Find the circuit. I think it's this one right here. Right there. So let's just take this 2-transistor circuit in MOS and go ahead and just analyze this using our small signal analysis, just to get a sense of how different it might be from the bipolar case, if at all. And so for this, this is an MOS circuit. I'm going to have some kind of bias voltage here. I'm not showing the full bias circuit here. But say I've got a bias voltage right there. I've got power up here. And so in order to solve this problem, it's exactly the same sequence that we use for bipolar. I'm first going to take this circuit up here and turn it into a small signal circuit. Okay, and so with this small signal circuit, what am I going to get? I'm going to have to repeat my V sub S voltage here, but I'm going to ground it out there. This capital V capital S right here goes away. And then I still have my source resistance, RS there. That's going to feed into my MOS transistor. That's going to go into an RD1. This was grounded here. And then I'm going to go all the way out here to an output device, which is tied sort of in a common drain, similar to a common collector. And if this is device 2, M2, then that would be RS2. And then finally I'll have this voltage right here. So this is my small signal circuit that I've created. And so let's just do the inspection analysis on this. And immediately I can write my input resistance is infinity, because that's just what it is. It doesn't change for MOS. I want my output resistance here. I'll have to look at the resistance scene looking that way, the resistance scene looking down that way, and putting them in parallel. And so this output resistance, I can come down here and just say that R0 is going to be equal to that RS2 that I'm going to see there. I should put a line down that S. I'm going to be complete and do it. Okay. And then that's going to be in parallel with what I see looking up through M2. And remember, for bipolar, I have to worry about what this resistance scene looking that way is. For MOS, I don't. It's just 1 over GM for that. And so specifically here, it's 1 over GM2. And so usually that's a small number, and so I'm just going to say this whole thing is just equal to 1 over GM2. So right away, I already have my input and output resistances. And so now just continuing here to get gains. And so if I want my gain, I'm going to do the same thing that I did before with bipolar. I'm going to identify some nodes. So if I identify this as node 1, that'll be node 2. This is my output node, so I won't even bother to call it node 3. I can just say that V0, let me go blue here to stay consistent. I could say that V0 over Vs is just going to be equal to Vs to V1, so this gain, times the gain from V1 to V2, times the gain from V2 to V0. So I need these three gains, and so I can write these three gains. The first gain, I've got RS going to a voltage divider into infinity. That's 1. Okay, the second gain is just the gain of now what I'll call a common source, same as a common emitter pretty much. And so I've got no emitter degeneration or anything on that, so that's just going to be GM of 1 times RD1. And then finally, this last gain that I have, I can write as RS2 divided by 1 over GM of 2 plus that RS2. And so in the end, that becomes my gain V0 over Vs. And very quickly, using inspection analysis, because MOS is so much easier than bipolar, basically I didn't have to worry about any loading resistance and that sort of thing, because they basically go to 0 because beta goes to infinity in a lot of my equations. I'm done. So I just did the mid-band analysis here, and I was talking doing this. It took me a couple minutes, but in reality I could have done the whole thing in just 1 minute or less, all of the stuff. So that's great. This is the gain equation that we end up with. But let me just say, if you look at this, the way that I've drawn this circuit now, I have not shorted my source to my bulk here. Okay? So I did nothing of the sort there. I'm going to keep going, by the way, so if you have to leave at 3, I'm just going to keep going until I do the full lecture because we lost all that time back there. But anyway, one problem that we have with this, if we apply this technique on this very circuit here, is that if you simulate the circuit using SPICE, let's say we simulate via SPICE, what happens? The gain that we get will not be equal to what we have in this equation above. In fact, it'll be 80 to 90% of what is calculated using the above. Right? So basically that equation is wrong. And the problem that we have is the GMB. That other GM that we have for MOS that has to do with the VBS voltage. So VBS for M1, there's no question here. Usually what happens is you tie the VBS, or you tie the bulk voltage, I guess this is already blue, to ground. And so that's what you're doing to this transistor here. And you're doing the same thing to this transistor, going all the way down to ground. For M1, no issue. Right? Still VBS is 0. But now for M2, VBS is not 0. It's a finite voltage now. And so because we're ignoring that, using our inspection formulas now, we end up having this issue, this problem here. And so the problem is with that GMB, but specifically in this circuit, it's with GMB in the source follower, the second stage. Not a problem for the first stage here. Okay, but of course GMB, right, this is the difference between bipolar and MOS, specifically between the bipolar and MOS hybrid pi models. Okay, and so because there's that difference in the models, the folly in what I'm doing is that I derived all these expressions up here for the case where the models were identical. Right? When I derived this and I derived these, that was for identical models. And they're identical models because I assumed that VSB was equal to 0. We have a question in the chat. Why can't the source and bulk be connected in M2 again? It can actually. You can do it. But the reason is that it takes more space on chip to do that. And space is money, basically. And so no one wants to do this. No one wants to tie the source to the bulk in this case because it costs you more money to do that. I'll talk about that at the very end of this. And so let me not talk about it just yet. Let me stay with what I'm talking about right here, that we're neglecting this GMB. And so let's focus on that source follower now with the substrate grounded. So in other words, VSB not equal to 0 volts. So in this case, what we're going to end up with is a circuit here that is, I'll just redraw my source follower here. I'll keep my source resistance RS here and have a voltage, an output voltage there, but now I'm going to explicitly show that I'm tied my bulk to ground here. And so what I want to do is draw out my hybrid pi model for this. Make sure I have enough space to do all this. I think I do. And so the small signal model for this is going to look like this. And I want to draw out my hybrid pi model because this is now going to be a situation that I haven't seen before. And I'm going to run out of space very quickly here, so let me sort of squish this in a little more here. I'm going to do a little bit of squishing here so I can keep my space. So I'm going to have that GM VGS there, and then I'm going to have my R naught. And just for kicks, I'm going to call that RDS because it's really a drain source voltage. I want to do that because in the end, well, no, let me call that GDS. Sorry, not RDS, but GDS. I basically want to work in terms of admittances instead of resistances here. That GDS is the same as 1 over R naught that we've been calling before. And then finally, I'm going to add in that other controlled current source here, which is going to be GMB times VBS there. And so this is in a source follower configuration, so the drain is going to ground. Down here, I have that resistance RS there. And that's where my output voltage is going to be. Okay, that's my source here. This is my gate. This is my drain here, of course. And this is where VI is going to be, and this is going to be the VGS that then is sourcing this current through this GM right there. So that's the small signal circuit that I've got here. But I got one more thing that I want to show here, and that's that I've taken my bulk terminal and grounded that. So I have a voltage between this V0 and that bulk terminal. That voltage across that, that's VBS. Okay? So I've got that VBS voltage there, and I guess I've got the polarities wrong there. Let me redo the polarities. Let me call this V out there and do this. This will be the plus polarity, the minus polarity for my VBS voltage there. Okay, so that's my small signal circuit for that. And so let's go ahead and solve this circuit. And so right away I can write a couple things. Let me do this in red. So first of all, this RS, since I want to work in conductances here, just because it's going to be easier to add things up a little later on, I'll call that 1 over GS there. And so this thing here, let me put this in red here. That's a 1 over R naught. GDS is 1 over R naught. And so from all of this, I can immediately write that VGS is just going to be equal to VI minus V out. Right? You can see that right across here. If this is VI right there and that's V out there, I guess you can't even tell that's VI, so let me rewrite that to make it look like a VI. So I have VGS equal to VI minus V out. I also have VBS. That's just equal to V naught, or minus V naught, because of the polarities that I've drawn there. Okay, so with this backdrop, I can now just write some equations here. So right away I can write that GM times that VGS, so that's going to be GM times VI minus V naught. That's going to be equal to, and that's this current running through here, that's going to be equal to the current going through RS, and the current going through GDS, and the current going through this GMB right here. So I'm going to say that that's equal to all those currents, because all the currents going into this node have to be equal there. So I can end up saying that this is going to be equal to V naught times GDS plus capital GS plus that GMB on that side. So in the end, I have an expression for my gain, which is V naught over VI, which is then just going to be GM over all these other GMs. Well, that same GM plus these other GMs, plus GMB plus GDS plus G sub S. Okay, that ends up being my gain equation there. But then I have a couple things that I can do. So that's the gain equation, but I know usually I neglect things, and so I'm going to neglect the same things that I neglect for bipolar quite often. I'm going to neglect this 1 over R naught, which is the same as GDS. That's the same thing as saying this GDS is much smaller than these other GMs here. But first, let's take a look at a special case here. Let's take a look at the case where, say, this RS is a huge resistance, and usually, right, if we have the ideal case, that's what would happen. So if I take RS, sorry, make that red here, and let that go to infinity here, that's the same thing as saying that GS is going to 0. And that's the same thing as saying that we're looking at this circuit. So we really replace RS with some current source IS here, because that has RS equal to infinity in that case. And so same problem we're looking at. That's still ground right there. We're sort of now, right, when we do this, we're really creating this situation. And you'll see later on that that is the way that we usually try to implement MOS amplifiers, or at least source followers like this, when we're completely on chip. We make a current source here, where that current source is actually coming from another transistor. So the way this really looks like is this. Okay, we're really creating this circuit, where that's VI, this is V out. And this is some kind of bias voltage here that's biasing the whole thing. I guess what I'm saying very quickly for you, and see if you can remember it for later on when you take 140, that is the same as that. The way that we implement current sources is using transistors like that. I showed you this a little earlier in the class, and I might show you it at the end if we have time. But if we don't, at least you've seen this right here. And if you didn't understand this, don't worry about it. You'll get it in 140 too. But I'm just saying this is a typical thing that happens. You take RS to infinity here, which means GS goes to 0. The other thing we can see from this usually is that this is 1 over R naught. R naught is very big. So usually GDS is going to be much less than GM plus GMB that you have in the denominator of this gain equation that I have. So with these two qualifications here, if I take this together with the gain equation I had on the other side, what I then end up with is a gain equation A sub V about equal to GM over GM plus GMB. That looks like an M. Okay, which often is written as, and you'll see this, 1 over 1 plus eta, where eta is equal to gamma, which is that body, which is that body factor that you had in your threshold equation, divided by 2 times the square root of VSB, that DC bias voltage VSB, plus 2 phi f, where you can see that these elements here come from the threshold voltage equation. Right? So let me just label this thing here as the body factor. From the threshold voltage equation that we've been using before. And so in the end, this is what the gain really is. It's not what we had before. Remember what we had before? If I move it up here, we had this. RS2 over 1 over GM2 plus that RS2. And so, or I could say it's this equation here if I want to keep that RS. I guess that still has an RS there. But if I made that RS infinite in this case, this would go to 1, right? Even if I made RS infinite, which is what I did here, this does not go to 1. So let me just come out here and write that on this side here. If I made RS infinite, this term goes to 1. Okay, but if you notice down here, this term right here, this gain, that's not equal to 1, no matter what you do with RS. Okay, you cannot get that to 1. Okay, to make it 1, you'd have to do with what we assumed up here. You need to do this. Where you take your transistor and you tie the source to the bulk. If you do this, you can get a gain close to 1. But like I said, this is not always practical. And now the reason why it's not always practical. The reason why it's not practical and people often don't want to do this, I said, was an area reason. And so here's a picture depicting what you would have to do in order to make this work. So say you were doing a CMOS process, and so you know what a CMOS transistor looks like, or an NMOS transistor looks like. You have an N plus junction, another N plus junction, you have a gate right here. And usually what happens in a CMOS process, if you've got NMOS devices, you've got PMOS devices in this as well. And so if you wanted to isolate this device, if you wanted to tie its source to its bulk, so let me go black on these terminals here. Right, so this is my gate terminal. Say that's my drain, that's my source, that's my bulk. What you'll effectively be doing is tying these two together. And you can do that if you made your transistor like this, and you put everything in its own P-well, like you're seeing right there. The trouble with this is that if you wanted to do this for all transistors, the next transistor, that's an NPN transistor, would have to be in its own P-well. And so I could have a transistor here that, say, has its P plus there, has N plus, another N plus, and another gate there. And if you want your transistors to have their own P-wells, then you're going to have a minimum distance here. Permissible distance between your P plus junction and the edge of this P well that then, of course, goes into this N-type material here. So everything out here is N-type. Okay, and you also need to have a minimum distance then between these two P wells. Okay, they have to be minimum because I'm assuming that you have two different voltages on there. You can't get these any closer. Whereas if you put all of your transistors into one well, you can get them a lot closer. And so all of that, as opposed to this situation, where I have one transistor here, and I can put another transistor right here, very close to one another, without having to have that large gap between them. And I'm able to do that because all of them share the same well, which I tie to ground. Okay, so this is the situation where we're actually tying this to ground. That's that situation here. And you can see I can get these devices a lot closer together than I can get devices that have to have their own well. That's why you don't like to do this. In order to do this, you have to have your own well. So the device needs its own well. I'll say P wells, it's an N-type device. And this takes space, which is shown right there. It's that above as opposed to this down here. I'm trying to write fast, so I saw that that was unreasonable, as opposed to this down here. Okay? So this is one of the issues we have to talk about. And what you're noticing here is the difference is this, there's a GM plus GMB added to this whole thing. And so in the end, you know, without doing all the derivations for you here, I'm just going to skip to the end and just tell you that this is what you end up with when your substrate is grounded instead of tied to your source. Okay, the only difference here is that a lot of the GMs in the denominators are replaced by GM plus GMB. And you can sort of see that that's got to be the case just from the look of the circuit here. The only thing I added with this GMB, you can see that they're kind of adding together. They have different voltages, VGS and VBS. But in a lot of cases, those voltages become the same when we're looking up, say, from the emitter there. So the formulas that you end up with are the formulas that we had before. And let me go back to the formulas before and show you those. So here's some of those formulas for MOS we had before. RG is still infinity. RS, that used to be 1 over GM, now it's 1 over GM plus GMB. Okay. RD, that used to be R naught times 1 plus GM times RS, that's now 1 plus GM plus GMB times RS, and so on and so forth. You see in instances where you have things in the denominator, not this in the numerator here, but also this right here. I guess there is no numerator or denominator right here. But these equations for gain also compare them to these equations. The only difference here is that GM plus GMB is being used down here instead of just GM there. This whole GM becomes GM plus GMB, and so on and so forth. You know, well, not so on and so forth, but for this last gain, you also get a GM plus GMB. Okay? Now, in a lot of cases, like I said, GMB is neglectable. So for a lot of the cases that you're doing, especially with the MOS transistors we had in lab for this class, you can neglect it. But when you start going to short channel devices, which is something that often happens, well, something that's plain and simply people are designing with short channel devices today, that GMB becomes more important. Okay, so that's why when you learn this stuff, I want to make sure that you learn it with this GM plus GMB in there. Right? For this class, it's not going to matter much. But for future classes, it will matter to some degree. Okay? And so as a final thing, what I want to do, you know, now that you know all of those equations there, let's do a final inspection analysis here We already did gain and the resistances. Let's now just do the high frequency analysis for this. And so to get high frequency analysis, I am just going to be lazy and just grab this. So I can just duplicate it where I want to do the high frequency analysis. Right here. So let me first write what I'm doing. So this will be MOS, high frequency inspection analysis. So again, I'm just going to plop that circuit down here. And let's just go ahead and do that analysis. I guess I need to erase this stuff first. But I'm going to keep all of my Okay, I'm going to keep all of my other stuff there. All of the nodes that I identified there. Ooh, I killed this resistance, didn't I? And so now let's go ahead and do this analysis. And so, starting off, I have my nodes. I need to put in my capacitors. And so for MOS, remember we have a CGS, so I have a CGS1. I have a CGD capacitance for 1. I'm going to have a CSB capacitance here. And I'm going to have a CDB also out here for that device 1. I've got those same capacitances for device 2, CGD2, CDB2, CGS2, and a CSB2. Okay, so those are my MOS capacitors right there. I'm going to want to eliminate as many capacitors as I can before I even start. And so right away I see this CDB2 out here. It's got ground here, it's got ground at that end. I'm going to eliminate it. Okay, any other capacitors that I can eliminate in this? Well, this CSB1, ground and ground, eliminate it. The CGD1, I don't want to have to memorize that driving point resistance for a feedback capacitor, so I'm going to go ahead and convert this to Miller capacitors. So I have a Miller capacitor here. CM1 is going to just be CGD1 times the gain of this thing, 1 plus the gain of this thing, and we know the gain of this thing already is GM1 times RD1 for that stage. The other Miller capacitor out here, CM2, I guess I have to say CM1 too because I have 2 transistors in this, and CM11 there. This is just going to be equal to CGD1. Okay, so those are my capacitors that I have to work with there. Let's now go ahead and do the total analysis. I'll go for blue in this case. And so I want my first time constant at node 1. That's going to be all that capacitance in shunt with node 1. So I can see that I have a CGS1. That is this capacitance going to ground right there. I've got this Miller capacitor here, which is CGD1 times 1 plus the gain. That's why that's a big capacitor now, because I just multiplied it by the gain. And that's going to be multiplied by all the resistance I see at that node. For bipolar, I'd see an R pi there, but for MOS, all I see is that RS. Very simple. Second time constant associated with node 2. So this is just going to be all of the capacitance that I see there. I see a CGD1 coming from that Miller effect. That's going to ground. I see that CDB1 that was also going to ground. And then I see another capacitor going to ground up here, which is that CGD2. That's my capacitance. Now I've got all the resistance that I see here. I see infinite resistance going into the gate of M2, so I'll ignore that. I see R0 of 1 in parallel with RD of 1. And so in this case, if RD is a physical resistor and not the resistance of a transistor, I probably can neglect that R0 of 1. So I'll go ahead and do that. Let me do that in another color so it doesn't completely mask that R0 1. Okay, and so I've got my second time constant there. Now I want my third time constant, Tau 3. Now I want all the capacitance hanging off of that output node, and all that capacitance and that output node is just CSB2. This capacitance, CGS2, that's in feedback. I can't really handle that as a shunt capacitor there. I have to have memorized that particular driving point resistance, but at least for CSB2, I've got this RB2 in parallel with this resistance seen looking up into the source of M2. That's just going to be a 1 over GM2 plus GMB of 2. Now I'm taking into account the fact that the bulk is not tied to the source in this case. So that's my third time constant. Finally, I've got this last time constant that has to do with the CGS2. And that's something where I just have to have CGS2. I just have to have that equation memorized here. And so I have that equation memorized. It's going to be the two resistors, this one and that one. I said B, that should be S. Sorry. It looked like a B to me when I looked at it. That's an S. Okay, and so these two resistors, RS2 and RD1, they still are there. So I have RD1 and RS2. Resistors hanging off of the gate and the source now. Divided by now this 1 plus GM2 plus GMB of 2 times RS of 2. Okay, and that now becomes Tau GS2. And in the end, it's the same procedure as always. If I want my omega H, my cutoff frequency, I'm going to take 1 over all of these time constant components. That then becomes my time constant. So very quickly, I have written out a formulation, and I've done a sloppy job, so I'm trying to fix that there. And so what you could have done, like we did with bipolar, so just to reinforce this CGS2, now we know that because this thing is going to ground here, instead of being tied to the bulk is not tied to the source there, then I'm not going to get a gain of 1 across this. So that CGS2 is still there, but for all intents and purposes, for most cases, I'm going to ignore that still, right? And I'm going to ignore that because there's very little signal across CGS2, since the gain is not 1, but it's close to 1. Okay, the stage gain is close to about 1, so there's no voltage across that. This is that same effect that we were looking at before. If I have that CGS1 here, sorry, CGS2, and I have, let me go, oops. Okay. And I have some voltage Vx here. I'm going to have about Vx there, and because of that, that CGS2 is just not going to show up there. Okay, so that is the high frequency response for an MOS example. And so now I've pretty much done an MOS inspection analysis. You see that it's very similar to bipolar. It's actually simpler. And so for MOS, small signal analysis is simpler than bipolar. However, for MOS, biasing is more difficult than bipolar, as we talked about before. You have to calculate more things. You have to deal with more nonlinear things. In bipolar, you could just say VBE on is 0.7 volts. In MOS, you can't quite say the same thing about VGS on, because bipolar is exponential. MOS is just going as a square law in terms of its current. It's a current response. Okay, so with that, that's it for this lecture. I guess I'm going to concatenate or put together these two lectures, the one that failed and then this one, and so you'll get a complete lecture online. But at least you four actually hung in there and watched all these lectures, which I appreciate. That's cool that you did that. But no more lectures for the rest of this week. I'll see you on Monday after your Thanksgiving break. So everyone have a nice Thanksgiving break, and I'll see you again on the other side.